Okay, so let's continue moving through equilibrium and how to solve equilibrium problems. Just to kind of recap what we just did, or at least some of what we just did. The first thing we would do with solving equilibrium problems is to write the balanced chemical equation. A lot of times this will be given to you, but it won't always, so it's going to be your job to pay attention to that. From there, the first thing I would do is to write the equilibrium expression. Remember, this is your K equals products over reactants raised to their coefficients. I would then list the concentrations. This would be done, personally, in my opinion, while I'm doing the ICE table. ICE, there we go. I would list my initial concentrations in there. Now, if one of our concentrations is 0, we know it has to shift that direction because 0 cannot exist in an equilibrium problem, okay? Cannot exist. So if we have a 0, we know it's shifting that direction. Well, what if we don't have a 0? That's where we calculate our handy-dandy Q value, which remember is getting calculated the same way K is, but it's just a snapshot to see are we at equilibrium? If we're not, which direction does it shift? And then we can determine the shift in our ICE table from there. So then we defined the change that needs to change. We define the change that needs to happen to reach equilibrium. This is where we subtract x or add x or 2x or whatever it happens to be. So this again will happen in our handy-dandy ICE chart. From there, if we have equilibrium values, we can substitute those in or put them in, or we can solve for the unknown as needed. So basically we use our equilibrium expression, plug in the values we do know, solve out from there, and then we can double check using our K values. So let's take this and actually work through another problem, kind of using these series of steps. So this problem, we are assuming that gaseous hydrogen iodide is synthesized from hydrogen gas and iodine vapor at a temperature where the equilibrium constant is 1.00 times 10 to the second. We're then told that we have hydrogen iodide at 5.00 times 10 to the negative 1 atm, hydrogen at 1.00 times 10 to the negative second atms, and iodine at 5.00 times 10 to the negative third atms, all mixed in a 5-liter flask, and we're told to calculate the equilibrium pressures of all the species involved. So our first step is going to be to write our equation, our balanced chemical equation. So we have hydrogen iodide being synthesized from hydrogen gas and iodine vapor. Okay, and that is forming gaseous hydrogen iodide, and of course with balancing we end up with this. So easy peasy. We're then told we have these initial concentrations, and we're told our K value. So if I was going to write my equilibrium expression, which is actually my next step, these are all gases, so it would be HI to the second over H2 and I2. Okay, and of course we can replace K with its actual value, which is 1.00 times 10 to the second if we want to, or we can just leave it as K and we can come back up here and grab it from the problem. Either way works. From there, we're asked to calculate the equilibrium pressures. This is where that ICE table comes in handy, and it kind of helps us just organize our thoughts and figure out what we're doing. So let's go through and plug in what we know, and we can leave it in ATMs because this is actually going to be KP, pressure. So we are told we have hydrogen iodide at 5.00 times 10 to the negative 1 atm. We're told we have hydrogen at 1.00 times 10 to the negative second, and we're told we have iodine at 5.00 times 10 to the negative third. So this is kind of an interesting situation. We have a value for all three of these. A lot of times we'll end up with a 0 for one of them, which a 0, again, can't exist in an equilibrium problem because that's not an equilibrium. Equilibrium has to have everybody, the rate of the forward equaling the rate of the reverse, and if somebody is 0, those collisions aren't occurring, so therefore it has no rate. It has to shift towards that direction to get rate. So in the scenario here where we've got something on all sides, we can't assume which direction it's going to shift, meaning I can't assume it's going to form reactants or products. So instead, I actually have to calculate out my Q value, which remember Q, mathematically, is the same expression as K. So I'm going to take my HI, which is 5.0 times 10 to the negative 1, square it, over my 1.00 times 10 to the negative second, times my 5.00 times 10 to the negative third. So take a second and solve for your Q value really quickly, and I want you to try to predict which direction this reaction is going to shift. Okay, so when I go through and do this math, what I'm getting is my Q is 5,000. And if we want to think about K, KP is 100. How does Q compare to K? Well, K is significantly smaller than Q. And remember, Q and K are both just products over reactants. So what's wrong with Q? Why is it so big? Well, because my products are too big, or my reactants are too small, however you want to think about it. So what's going to happen? My numerator is going to have to shift towards my denominator. My denominator must get bigger, my products, or numerator, must get smaller. And also remember, if we put these guys in alphabetical order, K first and Q second, it points in the direction which is going to shift. So it's going to shift from products to reactants. So what does that mean for our ICE table? What that means is I'm going to be making my reactants, and because of my stoichiometric coefficients, I'm going to be making 1 hydrogen for every 1 iodine, but I'm going to be using 2 of my hydrogen iodides because, again, coefficients. So at equilibrium, I end up with 1.00 times 10 to the negative second plus x, 5.00 times 10 to the negative third plus x, and 5.00 times 10 to the negative 1 minus 2x. So if I was to plug this into my equilibrium expression, I end up with 1.00 times 10 to the second equals 5.00 times 10 to the negative 1 minus 2x squared. Don't forget the squared. Sorry, I almost just did. 1.00 times 10 to the negative second plus x times 5.00 times 10 to the negative third plus x. And I'm hoping you guys are all groaning internally right now, because to solve for x, what's going to be required here? Hopefully you said the quadratic equation, because if we actually solve this out, I end up with FOIL, so I end up with x squared on both the top and bottom. I then have to multiply the bottom across, do all that stuff, simplify it into some type of basically x squared plus x minus whatever's left over, the digit there, and then plug it into my quadratic expression to actually solve for x. So here's the bad news. Equilibrium problems will actually require you to use a quadratic equation, which if you have that on your calculator, no big deal. The good news is when you take the AP exam, because the quadratic equation is kind of hefty and time consuming, especially if you don't have it on your calculator, they will not require you to actually solve a problem using the quadratic expression. So that's kind of the beauty of it. So the type of questions they might ask for this problem is, which direction is it shifting? Well, it's going to shift towards the reactants. Otherwise, you would have some type of x value to be able to plug in here to solve for something, whatever that happens to be. But the nice thing is we will actually never have to use the quadratic function to solve these problems. So what do we actually end up doing? Well, let's check this guy out. If k is very small, which it has a tendency to be for these types of problems to allow us to not have to use the quadratic function, if k is very small, we can determine the change is negligible. So let's look at this guy and kind of figure out what in the world am I talking about. So we have gaseous, NaCl, decomposing into gases, NO, and Cl2. And in terms of balancing, I'm going to need a 2 here and a 2 here. We're then told we have our equilibrium constant is 1.6 times 10 to the negative fifth. So that's really pretty small, 10 to the negative fifth. And if we think products over reactants, what that means is a lot of it's going to stay in reactants. We're going to have a very small shift towards products. We're also told that we're only starting with 1 mole of NaCl placed in a 2-liter container. So our original molarity for this guy is going to be 0.5 molar. So if I do my ICE here. And what that means is that I have 0 of these guys. So again, if I have 0, I automatically know which direction it's shifting. Not too bad. So this is going to be minus 2x, because 2x of these are going to be used. This is going to be plus 2x. 2x of these will form, and plus 1x. So at equilibrium, I end up with 0.5 minus 2x, 0 plus 2x, and x. And if I solve this, or if I plug this into my equilibrium expression, which again, k is 1.6 times 10 to the negative fifth, which is that guy, equals products 2x squared over x over 0.5 minus 2x. Now here's the problem. If I leave it set up like this, I still have quadratic coming down here. I still have to deal with a quadratic function. Or I can make an assumption. And that assumption can be k is very, very small. And that's actually not an assumption. That is a fact. K is very small. Well, if k is very small, how much of our reactants is actually turning into products? Not very many. So what is the actual difference between 0.5 and 2x? Essentially, it's going to be equal to 0.5 because 2x is going to be very, very small because k is very small, so very few products are forming. So what we can do now is simplify our math a little bit and just end up with 0.5 down here. So what does that actually give us? It gives us 1.6 times 10 to the negative fifth equals 4x cubed. So just in case you didn't follow that, that 2 goes to the 2, so 2 squared is 4. 2 becomes 4. X squared becomes x squared times x becomes x cubed over 0.5. Now, that's a whole lot easier to solve. So take a second and see what you can come up with here. Okay? And what I'm getting is my x value is basically looks like we've got 2 sig figs is what I would go with. So 1.3 times 10 to the negative second molar. So again, pretty small. What do we do with this from here? Well, we're being asked to find the equilibrium concentration, so all we have to do is take this guy and plug it back in for all of my x values. So what I end up with is chlorine is x, so it is 1.3 times 10 to the negative second molar at equilibrium. This guy is 2x, so 2.6 times 10 to the negative second molar. And this guy is 0.5 minus 2.6 times 10 to the negative second. And what does that actually give us? Well, when I go through and do the math, I end up getting 0.47. Okay, well, how different is 0.47 mathematically to 0.5? Very minimal, okay, and this can be even smaller depending on what size our k value is. So this is why we're able to make the assumption in terms of our math. Now keep in mind, I did go back through and unplug my x up here in my ICE table to solve for my equilibrium values, because is 0.5 actually changing? Yes, but is it changing significantly? No. This is the assumption we're making in our math, is that 0.5 mathematically is going to be still around 0.5 mathematically. So to be able to solve for it without using the quadratic function, that's basically what we're doing. But I still have to actually calculate out my concentration because, again, 0.5 isn't actually staying 0.5. It is changing. It's just changing very little. Okay, so we're going to stop here for this video, and we're going to continue working on through. Thanks so much, guys.